Hello again and welcome back to our course on Excel 2019 Advanced. In this section, we're going to continue looking at forecasting and we're going to be looking at linear regression, but in this case, we're going to use the LINEEST function. Now, the LINEEST function offers a number of advantages, and the first of them that I'm going to concentrate on is not only can it forecast values for us, but it can also indicate how likely it is that those forecasts are going to be good forecasts. It does this by evaluating how close the model that it's using is to the observed values that we're providing it with. The second advantage is that the LINEEST function can be used in multivariate regression. In this section, I'm going to demonstrate the LINEEST function with a single independent variable and a single dependent variable. And then in exercise 4, you're going to do some multivariate regression. But don't worry about that too much at the moment because hopefully you'll find it more straightforward than it sounds. Now, on the very subject of it being a little easier than it sounds, although I'm going to explain quite a few aspects of this as we go along, I'm also going to refer you to a page in the Excel 2019 help that explains what's going on in quite a lot of detail. Now, if you're not particularly interested in statistics or your maths is not quite up to scratch, you really don't need to worry too much about all these details. What we really need to be able to do is apply the method, and the help sets out pretty much how to apply that method. Now, referring back to the preceding section, the first method that I showed you there involved finding the slope and the intercept for the best fit straight line through some pairs of values. And pretty much that's what LINEEST does as well. It gives you a slope and an intercept. But it can give you multiple slopes based on the use of multiple variables. So I could have, for example, a number of independent variables, and there will be a slope associated with each of those. Now, when we actually use the LINEEST function, we apply it as an array formula. And before I use it, I need to know how many rows or how many columns I need to select. Now, the number of columns will be the number of independent variables plus 1. So in this case, x is my independent variable, and therefore I need 2 columns. The number of rows I need, well, I would need 1 row for the slope value, and then if I want all of the additional underlying statistics, I need 4 rows for those. I'm going to look at those statistics, so I'll need a total of 5 rows, 1 for the slope and 4 for the statistics. So I'll need to select an area that has 2 columns and 5 rows. So I'm going to select E3 to F7. Now I'm going to use the LINEEST function. Now, the first value that I put in there are the known y's, so that is C3 to C14, and we'll make those absolute. Next, I put in the known x values, so that's B3 to B14. The third value is the one we talked about in the previous section, and if we expect to have a non-zero intercept, we set this to true. And the fourth argument indicates whether we want the additional regression statistics or not. Now, we are going to look at those additional regression statistics, so that's going to be true as well. Having entered LINEEST and bearing in mind that this is an array formula, we need to do Control, Shift and Enter. And there are my values. Now, the first thing to note is that E3 and F3 hold the slope and the intercept. So if all I want to do is to predict the value of y when x is 13, I can use one of the methods that I showed you in the preceding section. And fill down. And once again, the same values have been predicted, but what's particularly helpful and useful here are the other values, the ones in the range E4 to F7. And in order to understand, particularly the contents of E5, we're going to go and look at the help for the LINEST function. Now, there are quite a few things I want to point out about the LINEST function, as it's a very useful and important function in Excel 2019. And the first thing to point out is that you can use it with other functions to model relationships that are not straightforward linear relationships. So as it says there, you can include polynomial, logarithmic, exponential, and power series relationships. Now this has to be done in a particular way, and there is more information about this in this help topic. I'm not going to cover that in this course, but you may be in a situation where you have a relationship that is not a simple linear one, where there is some element of it that includes one of those other types of relationships. Well, LINEST can cope with that kind of situation as well. Now, in the preceding section, we looked at the straightforward y equals mx plus c. It's normally denoted, although in the help here, it's y equals mx plus b, but b is the intercept. Well, the situation with LINEST is that you can make y dependent on many x's, and if you do make it dependent on many x's, then for each x, there will be a slope. So, for example, in exercise 4, I'm going to give you some data with two independent variables in it, two x's, and you'll get two slopes. But more on that later on. Now, when you use the LINEST function, I've already talked about the syntax, and you've seen one use of it already. There's a further explanation of it there, and in particular, it covers an explanation of the multivariate situation, which is going to be particularly important in exercise 4. Now, also, there's a list of statistical terms, which are very familiar to statisticians, but probably a mystery to most other people. So, terms like F statistic or the number of degrees of freedom. If you are a statistician or you understand these terms, they're pretty well explained in the help and related to that block of numbers that I referred back to in our sheet, Regression Functions 4. But what I really want to look at here is R2, the coefficient of determination. And what happens with the coefficient of determination is that it compares estimated and actual y values. Now, the closer to 1, the better the correlation, and by correlation we mean in simple terms how well the line fits against the data we first provided. If the provided data was an absolute straight line already, then the coefficient of determination would have a value of 1. If all the values seem random and unrelated, the coefficient of determination will have a value of 0 or close to 0. So what you're looking for a good match is a value that is near to 1. Now, with these other statistics, you may or may not be interested in them. The sum of squares, the regression sum of squares, again, I'll come back to that in a moment just for information, as I think it's something worth knowing about. But in terms of identifying what's in that array of numbers, this little diagram is the important one because it shows you what goes where. Now, in our case, we only had one independent variable, so we only had two columns, and column A in that diagram, that's our slope value in row 1, and the value in the third row in column 1 is R2. Now, below there is a whole load of remarks about how this works and how you can interpret things and so on. So if you are interested, it makes a very useful and interesting read. Now let's look again at that diagram because we are interested in the first column middle row. Now the value we have in there is 0.89 and the value of 0.89 is pretty good. That's a relatively high correlation. So what we're being told there is that there does seem to be a reasonable relationship between the y values and the x values. It's not brilliant, but it's about 90%, which is pretty good. Now there is one point I said I would come back to, and that's the sum of squares. I'm not going to explain this in any great detail. There's actually quite a bit of detail on that help page, but one relatively straightforward way of thinking of how it works is as follows. If you look at each of our x values here, so 1, 2, 3, 4 along the horizontal axis, and with each of them go up to the graph and the dotted line, which is the best fit straight line, for each value of x you will see there is normally a slight discrepancy between the value on the blue line, which is the observed y value, and the value on the dotted or best fit line. If you work out what the discrepancy is between the y values, so that's the blue line and the dotted line, and you square that amount and you add all of those discrepancies up, the way that the best fit is worked out is to make the sum of those squares as small as possible. So you're basically working out how to fit a straight line through those points such that the sum of those squares is as small as possible, and that's how the dotted line finishes up where it is. That's a somewhat oversimplified explanation of it, but it will give you some idea of how the best fit line is arrived at, and it will also explain how, for example, this coefficient of determination is calculated, because it's calculated using a formula based on that sum of squares. Now, in fact, all the documentation you will see that sum of squares referred to as R2. Statistically, it's more accurately referred to as r squared, and in the case of linear regression, r squared is actually the square of the correlation coefficient. And basically, you want r squared to be as close as possible to 1. So that's it for this section. Please join me in the next.